Welcome back to Science and Slumber. Tonight, we drift toward the most enigmatic and powerful objects in the entire universe: black holes. They are often imagined as cosmic vacuum cleaners, relentlessly pulling everything into their dark abyss. But the truth is far more subtle and awe-inspiring. These celestial objects are not monsters, but rather a natural, mind-bending consequence of gravity itself. Places where the fabric of space-time is stretched to its absolute limit, where time flows like a slow-moving river and from which not even light can escape. If these peaceful explorations help you unwind or spark your curiosity, consider liking this video and subscribing. Your small gesture helps others find their way to this quiet corner of the cosmos, a place for rest and wonder. Now, find a comfortable position and get settled as we embark on this gentle journey toward the silent, velvet darkness of a black hole. One of the most profound truths about a black hole is its power to warp the very flow of existence. Near its immense gravity, the steady, universal rhythm of time begins to falter. For an observer close to the edge of a black hole, time itself slows down dramatically compared to the universe far away. This is a core prediction of Einstein's theory of general relativity, which tells us that gravity is not just a force, but a deep curvature in the fabric of space-time. A black hole's density creates such an extreme indentation that it drags time along with it, forcing it to pass more slowly for anyone within its powerful influence. An astronaut who spends what feels like a few minutes near this gravitational well could return to find that years or even centuries have passed for everyone else. Imagine time as a vast, straight-flowing river. In most of the universe, its current is consistent and predictable, but a black hole is like a colossal whirlpool in that river, where the water spirals deeper and its flow becomes thick and sluggish. A clock floating near the edge of this whirlpool would tick far more slowly than a clock on the distant, peaceful riverbank. A black hole, therefore, does not just consume matter and light, it holds moments captive, stretching them into near eternity at the edge of its silent horizon. Should any object venture too close to a stellar black hole, it would undergo a process with a curiously gentle name for such a violent fate: spaghettification. This strange and powerful phenomenon occurs because the force of gravity is not uniform across an object. The part of the object closer to the black hole experiences an exponentially stronger pull than the part that is farther away. For an unlucky astronaut falling feet first, the gravitational tug on their feet would be immensely more powerful than the pull on their head, creating a differential that would stretch their body relentlessly. This immense tidal force elongates any object, whether it is a planet, a star, or a spaceship, compressing it sideways while stretching it lengthwise until it becomes a thin, flowing stream of individual atoms spiraling into the darkness. It is much like taking a soft piece of warm taffy in your hands and slowly pulling it from both ends. The candy thins out in the middle, growing longer and more delicate until it is just a fragile, sugary thread. Spaghettification is a stark and humbling reminder that gravity, the force that gently holds us to the earth, can become the most destructive and overwhelming power in the entire universe. At the very heart of every black hole lies its ultimate secret: a gravitational singularity. This is the final destination for all the matter and light that has ever crossed the event horizon, a place where the force of gravity becomes infinitely powerful. Here, the entire mass of a collapsed star, or in the case of a supermassive black hole, billions of stars, is crushed down into a region with zero volume and infinite density. Within this single, dimensionless point, our known laws of physics, the very rules that govern the cosmos, simply cease to apply, leaving us at the edge of a profound mystery. Imagine taking a colossal mountain, with all of its stone, soil, and sheer weight, and compressing it down until it fits into a space smaller than the sharpest point of a needle. The singularity is an even greater extreme, an object with immense mass but no physical size at all. It represents the ultimate boundary of our knowledge, a true cosmic enigma where the fabric of reality itself comes to an end. At the heart of nearly every large galaxy, including our very own Milky Way, resides a gentle giant of unimaginable proportions, a supermassive black hole. These are not the remnants of a single collapsed star, but are instead cosmic titans that have grown over billions of years to possess the mass of millions, or even billions, of suns. They are the gravitational cornerstones of their galaxies, the immense wells of gravity around which everything else, stars, gas, dust, and planets, revolves in a slow and graceful celestial ballet. Our own galaxy's silent anchor is known as Sagittarius A star, and its profound gravitational influence is what orchestrates the grand, spiraling structure of the Milky Way. Imagine a vast spinning web, glistening with billions of dewdrops, each one a star. At the very center of this intricate design is a single heavy weight that holds all the delicate threads in place, giving the entire structure its shape and stability. In the same way, these colossal black holes are the quiet architects of galactic order, their presence essential to the cosmic cities of stars we see scattered across the night sky. Every black hole is defined by an invisible, yet absolute, boundary known as the event horizon. This is not a solid surface you could touch, but rather a profound threshold in space-time, a one-way door into the unknown. It marks the precise point where the gravitational pull of the black hole becomes so overwhelmingly powerful that the escape velocity surpasses the speed of light. Since nothing in the universe can travel faster than light, anything that crosses this boundary, a star, a planet, a single photon, is forever captured, its journey now having only one possible direction: inward toward the singularity. Think of it as a boat drifting on a wide, calm river that quickens as it approaches the precipice of a colossal waterfall. There is a specific, invisible line in the water, beyond which the current becomes too swift to fight. Once your boat drifts past that point, no amount of rowing can save you. The waterfall's pull is inevitable. The event horizon is that final, silent point of no return, a serene and perfect sphere that forever separates the world we can see from the deep mysteries hidden within. A black hole possesses a gravity so profound that it can bend and reshape the very path of light itself, an effect known as gravitational lensing. This phenomenon doesn't just block light, it actively manipulates it, turning the black hole into a natural cosmic telescope. Einstein's theory of general relativity explains that massive objects create a deep well in the fabric of space-time. As light from a distant galaxy travels past the edge of this gravitational well, it follows the curve, much like a marble rolling around the edge of a bowl. From our vantage point on Earth, this bending of light can make the background galaxy appear distorted, stretched into arcs, or even multiplied into several distinct images arranged around the black hole. Imagine looking at the world through the thick, curved base of a wine glass. The glass itself is transparent, yet it warps and magnifies everything behind it, creating strange and beautiful patterns. In this way, the deepest darkness in the universe can paradoxically illuminate what lies beyond, bending light to reveal its own powerful and invisible presence. Despite their reputation as eternal, prisons of light and matter, black holes are not perfectly black. In a startling union of quantum mechanics and gravity, it was predicted that they must emit a faint, constant stream of thermal energy, a phenomenon now known as Hawking radiation. This theory suggests that the vacuum of empty space is not truly empty, but is instead a frothing sea of virtual particle pairs that spontaneously appear and annihilate each other in the blink of an eye. If such a pair comes into existence at the very edge of a black hole's event horizon, one particle might be captured and fall in, while its partner escapes into the cosmos. This escaping particle carries away a tiny fragment of the black hole's energy, causing the black hole to lose an infinitesimal amount of mass and shrink over incomprehensible timescales. Think of it as a faint, slow hiss of steam escaping from a colossal sealed vessel. Each particle that breaks free is like a single molecule of water vapor, carrying away a whisper of heat, and over eons, the vessel will inevitably empty. This subtle glow reveals a profound cosmic truth. Even the most powerful and seemingly permanent objects in the universe are subject to an impossibly slow and graceful process of decay. Contrary to the popular image of a cosmic predator, a black hole does not actively suck matter in like a relentless vacuum cleaner. Its gravitational influence is governed by the same universal laws as any star or planet, its pull determined solely by its mass. From a safe distance, a black hole's gravity is no different than that of a star of the same size. If our own sun were instantly replaced with a black hole of equal mass, the Earth and the other planets would continue in their exact orbits, undisturbed, though plunged into a silent, frozen darkness. The danger of a black hole lies not in an aggressive reach across space, but in the passive, absolute nature of its gravity. Once you draw too near, think of it less like a vacuum and more like a deep, silent drain at the bottom of a vast, still ocean. The water far from the drain feels no significant pull and continues on its own currents. Only the water that happens to drift directly over the drain's edge is captured by its gentle but inexorable downward spiral. This reveals that a black hole's power is one of quiet inevitability, not of cosmic violence, commanding only the space it immediately occupies. While black holes themselves are silent, the universe has provided us with a way to listen to their most profound and violent moments. Through the detection of gravitational waves, we can now essentially hear the cosmic ripples that spread across space-time when two of these immense objects collide and merge. Predicted by Albert Einstein, gravitational waves are minuscule vibrations in the very fabric of reality, created by the most cataclysmic events in the cosmos. When two black holes, locked in a final, frantic orbital dance, spiral into one another, their immense masses warp space-time so violently that they radiate these waves outward in all directions at the speed of light. These waves carry with them the unmistakable signature of their source, the story of the final moments of two cosmic giants becoming one. Imagine dropping two smooth, heavy stones into the center of a perfectly still, silent pond. From the point of impact, gentle concentric ripples spread outward across the water's surface, carrying the quiet story of the disturbance far from its origin. Gravitational waves are the cosmic equivalent of these ripples, but instead of traveling through water, they travel through the very essence of space and time. This remarkable ability to detect these faint cosmic echoes has opened up an entirely new sense for astronomy, allowing us to listen to the silent, dark symphony of the universe. Despite the immense complexity of the stars that create them, black holes are governed by a principle of profound simplicity known as the no-hair theorem. This idea states that once a black hole settles into a stable state, it can be completely described by just three external properties: its mass, its spin, and its electric charge. The name itself is a metaphor, suggesting that all of the other intricate details, the hair of the matter that created or fell into it, are lost forever. The specific type of star it once was, the chemical composition of the gas clouds it consumed, all of that unique information is wiped clean from the universe's view, hidden behind the event horizon. Imagine a master bell founder melting down countless different objects, a golden crown, an iron sword, a silver coin into a single massive crucible. Once the molten liquid is poured into a mold and cools, the final bell that emerges has its own distinct properties, but the individual histories of the crown, the sword, and the coin have vanished. This theorem reveals that a black hole acts as a sort of cosmic eraser, a perfect final state that retains no memory of the beautiful and chaotic universe from which it was born. While the idea of a black hole might feel impossibly distant, our nearest known cosmic neighbor of this kind is a silent wanderer named Gaia BH1. It lies approximately 1,560 light-years away, a distance that is vast by human standards, but remarkably close in the grand scale of the Milky Way galaxy. This particular black hole is classified as dormant, meaning it is not actively pulling in gas from its companion star, and, As a result, it does not produce the brilliant flares of X-rays that typically give away their locations. Instead, its presence was uncovered through a masterpiece of subtle observation by watching its sun-like companion star wobble in its orbit. The star moves as if it is being gracefully led in a dance by a massive, yet completely invisible partner. Imagine two ice skaters performing a perfect, synchronized routine in the dark, but only one of them is covered in glowing lights. Even though you cannot see the second skater, you could trace their exact path and even sense their presence just by watching how the illuminated skater spins, dips, and glides across the ice. The quiet companionship of Gaia BH1 and its star reminds us that the universe is teeming with hidden marvels, their presence revealed only by the gentle gravitational rhythm they impart on the cosmos around them. The fate of an object falling into a black hole is not a singular experience. It depends entirely on the scale of the cosmic giant it encounters. If you were to fall toward a stellar mass black hole, just a few times the mass of our Sun, the journey would end violently and swiftly. The intense tidal forces would stretch your body into a thin strand of atoms, a process called spaghettification, long before you ever reach the event horizon. However, if your destination were a supermassive black hole, millions or billions of times the Sun's mass, you could drift across its vast event horizon completely intact, without feeling any immediate change. The difference lies in the steepness of the gravitational curve. A smaller black hole has a very sharp, tight curve, meaning the difference in the gravitational pull between your head and feet is extreme. In contrast, a supermassive black hole is so enormous that its gravitational curve is far gentler at its edge. Imagine the difference between walking over a small, steep speed bump and cresting the peak of a mountain that is miles wide. The speed bump is a sudden, jarring change, while the mountain's summit feels almost perfectly flat as you walk across it. This reveals that the passage into oblivion can be either a brutal, sudden tearing apart, or a serene and silent crossing into the realm of the unknown. Long before the language of space-time and general relativity existed, the first whisper of the idea of a black hole came from an English natural philosopher named John Michell in 1783. Working with the physics of his time, he imagined light not as a wave, but as a stream of tiny particles, or corpuscles, as Isaac Newton had suggested. He reasoned that these particles of light, just like any other object with mass, must be affected by the pull of gravity. Michell then performed a thought experiment, calculating that if a star were sufficiently massive and dense, the escape velocity from its surface would be greater than the speed of light itself. Any light emitted from such a star would be immediately pulled back by its own immense gravity, rendering the star completely invisible to the outside universe. His idea was like imagining a cannonball being fired from the surface of a world with an impossibly strong gravitational pull. No matter how much power you put behind it, the cannonball would always arc gracefully back to the ground, never breaking free. This astonishingly prescient thought reveals that the concept of a dark star, a true cosmic prison for light, was born not from complex equations, but from the simple, powerful curiosity of a mind contemplating the fundamental forces of nature. For much of its theoretical life, this cosmic enigma had no simple name. Scientists labored under cumbersome descriptions like gravitationally completely collapsed object or frozen star. But in 1967, the American physicist John Wheeler, during a conference, offered a name that was as simple as it was profound: the black hole. The term was immediately captivating because it perfectly captured the two most fundamental properties of the object in a way that anyone could understand. Black described its nature as an object that absorbs all light and reflects none, rendering it perfectly invisible. Hole evoked the idea of a one-way journey, a deep well in the fabric of space from which there is no return. It was a piece of scientific poetry that stuck, instantly replacing the dry, technical jargon. Imagine trying to describe a vast, deep canyon using only its geological coordinates and rock composition. Then, Someone comes along and simply calls it the Grand Canyon. The right name doesn't just describe, it gives a concept, a soul, and a place in our shared imagination. With just two simple words, John Wheeler gave an identity to the unimaginable, forever shaping how we see and speak about these silent cosmic giants. When a massive object like a star collapses, it doesn't just retain its mass, it also carries its rotational energy into the resulting black hole. This creates a rotating black hole, known as a Kerr black hole, which doesn't just sit passively in space but actively twists the very fabric of space-time around it. This remarkable effect, known as frame dragging, is a direct consequence of Einstein's theory of general relativity, which shows that massive, rotating bodies can literally drag space and time along with their spin. Anything near this type of black hole, even light itself, is forced to move in the direction of its rotation, caught in a cosmic whirlpool from which it is impossible to stand still. Imagine placing a heavy spinning ball into a large bowl filled with thick, viscous honey. As the ball rotates, it doesn't just spin in place, it pulls the honey closest to it along for the ride, creating a swirling vortex that extends outward into the rest of the bowl. Frame dragging reveals that a black hole's influence is not just a simple pull downward, but a powerful dynamic dance that reshapes the fundamental geometry of the universe. The very first time humanity could point to a spot in the night sky and confidently say, "There is a black hole," was with the discovery of Cygnus X1. Identified in 1971, this object was not seen, but its powerful presence was undeniably felt. Astronomers using X-ray telescopes detected an incredibly bright source of high-energy radiation coming from the constellation Cygnus, the Swan. They soon realized these X-rays were originating from a system where a massive, visible blue supergiant star was orbiting an unseen companion. Gas was being violently siphoned from the surface of the living star, accelerating into a glowing hot accretion disk around the invisible object before it disappeared. By carefully studying the visible star's orbit, scientists calculated that its mysterious partner was far too massive to be a neutron star, the densest known objects at the time. The only explanation that fit the evidence was a true black hole. It was like seeing a single dancer on a grand stage, spinning gracefully as if held by a partner who was completely invisible. You could not see the partner, but from the dancer's perfect, steady movements you would know without a doubt that they were there. This discovery finally brought black holes out of the realm of pure theory and into the observable universe, marking the beginning of a new era in our cosmic exploration. Stellar mass black holes are born from the spectacular death of a single gigantic star, one that lived its life with incredible brilliance. This cosmic transformation occurs only when a star more than 20 times the mass of our own Sun reaches the end of its life. Throughout its luminous existence, the star maintains a delicate balance between the outward pressure of nuclear fusion in its core and the relentless inward crush of its own gravity. But when its nuclear fuel is finally spent, the furnace at its heart grows cold. In that moment, the outward push ceases, and gravity wins the final decisive battle. The core collapses catastrophically, imploding under its own weight and compressing into a point of unimaginable density. It is much like a skyscraper whose foundational supports have all vanished in an instant. The entire structure falls inward upon itself with unstoppable force, creating a single, infinitely dense point where its core used to be. From the ashes of a brilliant star's demise, a new and permanent silence is born into the cosmos. Among the cosmic titans known to humanity, one of the most astonishing is a supermassive black hole named TON 618. Located in a distant quasar, this object is a true behemoth, its mass estimated to be a staggering 66 billion times that of our own Sunday. It is so vast that it defies our everyday sense of scale, its sheer size challenging the limits of our understanding of how such objects can even form. The event horizon of this single black hole is so immense that our entire solar system, from the Sun all the way out to Neptune, could fit inside it more than 10 times over. Its presence was first detected not by seeing the black hole itself, but by observing the brilliant, superheated glow of the matter. It is consuming a quasar that shines with the light of 100 trillion suns. Imagine a single, silent whirlpool in an endless ocean, so vast and powerful that its spiraling motion can be seen from the farthest shores. TON 618 is such a vortex in the fabric of spacetime, a quiet reminder that the universe has an almost limitless capacity to produce wonders of truly incomprehensible scale. While a black hole itself is the embodiment of darkness, the region just outside its event horizon can be one of the most luminous places in the entire universe. This brilliant display is created by an accretion disk, a swirling, flattened carousel of gas, dust, and stellar debris that has been captured by the black hole's gravity, but has not yet fallen in. As this material spirals relentlessly inward, like water circling a drain, the individual particles rub against each other with incredible friction. This cosmic friction generates an immense amount of heat, causing the disk to glow at millions of degrees and radiate an astonishing amount of energy across the electromagnetic spectrum. In the case of a quasar, which is powered by a supermassive black hole actively feeding, this glowing disk can shine with more light than all of the hundreds of billions of stars in its host galaxy. Combined, imagine a spinning grindstone sharpening a blade in the dark. While the stone itself is dark and cold, the intense friction at the point of contact creates a brilliant, cascading shower of white-hot sparks. The accretion disk is a cosmic-scale version of this, a final, radiant farewell from matter on the verge of disappearing from the visible universe forever. For generations, a black hole was something that existed only in our equations and in our imaginations, an object that, by its very nature, could never be seen. But in 2019, that all changed. The Event Horizon Telescope, a global network of synchronized radio telescopes that effectively created a virtual observatory the size of our entire planet, captured the first ever direct image of a black hole's shadow. The target was the supermassive black hole at the heart of the galaxy, Messier 87, some 55 million light-years from Earth. The resulting image was not of the black hole itself, but of its silhouette, a perfect circle of pure darkness set against the glowing, superheated gas of its accretion disk. We were seeing the void, the outline of the event horizon, for the very first time. It was like standing on a brightly lit street at night and looking at the perfect dark outline of a person standing in front of a brilliant storefront window. You do not see their face or their features, but you see their unmistakable shape, their presence defined by the light they obscure. This historic achievement transformed our understanding of black holes from a beautiful theory into a tangible, observable reality, confirming a century of scientific prediction in a single, breathtaking image. One of the deepest puzzles in modern physics is the information paradox, a profound conflict born from the very existence of black holes. A fundamental rule of quantum mechanics insists that information about the universe can never be truly destroyed. It can only be rearranged. However, a black hole appears to violate this law completely. When any object, like a star, falls past the event horizon, all of its unique and intricate details seem to be permanently erased, with only its mass, spin, and charge being added to the black hole. As the black hole slowly evaporates over eons through Hawking radiation, this radiation is predicted to be random and thermal, containing no trace of what fell inside. Imagine writing a detailed story in a diary and then setting the book on fire. While the pages turn to ash and smoke, a physicist would argue that if you could perfectly measure every single particle, you could, in theory, reconstruct the original story. The information isn't gone, just impossibly scrambled. A black hole, however, is like a perfect incinerator that not only burns the diary, but seemingly erases the very concept of the story from existence, leaving behind only a faint, meaningless warmth. This paradox represents a deep and fundamental crack in our understanding of reality, suggesting that a more profound physical truth still waits to be discovered in the silence between gravity and the quantum world. Not all black holes are born from the death of massive stars. Some are thought to be ancient relics from the very dawn of time itself, known as primordial black holes. These are purely hypothetical objects, but the theory suggests they were formed in the first few moments after the Big Bang. In that chaotic primordial soup, the universe was not smooth and uniform, but was instead a turbulent sea of energy and matter. It is believed that in some tiny regions, the density could have become so extraordinarily high that these pockets of space collapsed directly under their own immense gravity, forging black holes without ever needing a star to live and die first. Imagine a vast, cooling pot of molten glass, still churning and uneven. As it hardens, most of it becomes a smooth, solid sheet, but a few tiny, super-dense impurities might collapse in on themselves, forming permanent, tiny flaws within the glass. If they exist, these ancient wanderers could be silently drifting through the cosmos, tiny, dark seeds from which the entire universe has grown. In the vast cosmic family of black holes, there exists a mysterious and elusive middle child, the intermediate mass black hole. These objects are the missing link between the relatively small stellar mass black holes, born from the collapse of a single star, and the supermassive titans that reside at the centers of galaxies. Possessing masses that range from a few hundred to a few 100,000 times that of our Sun, they are incredibly difficult to find because they lack the obvious telltale signs of their siblings. They are not typically found in the bright X-ray binary systems that reveal smaller black holes, nor are they massive enough to dominate the stellar orbits in a galaxy's core. Think of it as searching for a specific kind of stone on an endless shore. You can easily find the small common pebbles and the giant unmissable boulders, but finding a stone of a very particular in-between size requires a far more careful and patient eye. The search for these quiet, mid-sized wanderers is one of the great challenges in modern astronomy, as each new discovery provides a crucial piece of the puzzle of how the universe's greatest giants came to be. A star that wanders too close to the immense gravity of a supermassive black hole is doomed to a spectacular and violent end. It will be completely shredded in a celestial drama known as a tidal disruption event. This violent unraveling happens because the black hole's gravity pulls on the nearest side of the star with immensely more force than it does on the far side. This overwhelming difference in gravitational pull, a cosmic tidal force, stretches the star beyond its breaking point, overcoming the star's own gravity that holds it together. The star is torn apart, its constituent gas pulled into long, flowing streams, part of which spirals into the black hole, creating a brilliant flare of light that can be seen across the universe. Imagine a fragile soap bubble drifting too close to the immense, rushing power of a waterfall. The sheer force of the moving water would stretch and tear the bubble's delicate film, pulling it apart into mist and spray long before it could ever reach the rocks below. In this way, the star's catastrophic death becomes a brilliant, fleeting beacon, illuminating the silent gravitational sovereign that reigns, unseen, over the galactic core. Encircling the event horizon of every black hole is a thin, ghostly region of space known as the photon sphere. This is a place of profound gravitational balance, a cosmic knife's edge where gravity is so immensely powerful that it can trap particles of light, or photons, forcing them to travel in unstable orbits. If you were to send a beam of light into this region at a perfect tangent, it would be bent by gravity into a circular path, eternally orbiting the black hole just outside its point of no return. Standing within this sphere, you could theoretically see the back of your own head, as the light from it would travel all the way around the black hole and return to your eyes. This is like perfectly launching a satellite into orbit around a planet, where its forward velocity is in a constant, delicate balance with the planet's gravitational pull. The photon sphere is the ultimate expression of this balance, a place where light itself, the fastest thing in the universe, is held captive in a silent, gravitational dance just before its final plunge into darkness. Shortly after Albert Einstein published his revolutionary theory of general relativity in 1915, a German physicist named Karl Schwarzschild became the very first person to find an exact solution to its complex equations. He accomplished this remarkable feat while serving on the front lines of World War I, describing the precise geometry of spacetime around a single, non-rotating spherical mass. His solution revealed something astonishing. If enough mass were concentrated within a small enough area, the curvature of spacetime would become so extreme that it would effectively close in on itself, forming what we now understand as a black hole. He calculated the exact boundary for this phenomenon, a radius from which nothing could escape, a value that is now fittingly known as the Schwarzschild radius. Imagine being the first person to follow a new set of mathematical instructions for folding a piece of paper, only to realize that the final steps cause the paper to curve into a perfect, sealed sphere with no way to get back inside. Schwarzschild was that brilliant pioneer, a mind who journeyed into the deepest implications of a new theory and returned with a map to the edge of reality itself. At the very heart of our own cosmic home, the Milky Way, resides a colossal supermassive black hole known to astronomers as Sagittarius A star, pronounced Sagittarius A star. It is the gravitational anchor around which our entire galaxy, including our own sun and solar system, completes its long and graceful 230 million year orbit. Located about 26,000 light-years from Earth in the direction of the Sagittarius constellation, it is a powerful and compact source of radio waves, which earned it the asterisk in its name, a designation from physics that denotes an excited state. Although it has the mass of over 4 million suns, it remains completely invisible to our eyes, its presence revealed only by its profound influence on the stars that swarm around it in tight, rapid paths. Think of it as the silent, invisible hub of a colossal spinning pinwheel. All the beautiful, glittering arms of the pinwheel, dotted with countless stars, are held in their spiraling pattern by the stability of that central point, even though the hub itself is just a simple, unadorned pivot. This quiet giant is the calm and steady heart of our galactic family, its immense presence orchestrating our slow, silent waltz through the cosmos. In the asymmetric world of theoretical physics, black holes have a purely hypothetical and fascinating twin known as a white hole. It is a mathematical possibility born from the same equations of general relativity, representing a perfect reversal of a black hole in time. While a black hole is a region of spacetime that can only be entered and never exited, a white hole is a region that can only be exited and never entered. It is theorized as an object that would violently and spontaneously erupt with matter and energy, spewing out information that had no discernible origin. Some speculative theories have proposed that if you were to fall into a black hole, you might emerge from a white hole in a completely different universe, or a different point in our own space-time, forming a kind of cosmic bridge. Imagine a one-way door into a room. That is the black hole. Now, picture a second door on the opposite side of the room from which people are constantly emerging, but which can never be opened from the outside. That is the white hole. While there is no observational evidence to suggest that white holes actually exist, they remain a tantalizing and poetic possibility, a reminder that the universe's most profound truths often begin as a beautiful idea in the quiet landscape of a theoretical mind. The fundamental reason a black hole is completely dark is a simple yet absolute cosmic law. To break free from its immense gravitational pull, an object must travel faster than the speed of light, a feat that is impossible for anything in the universe. Escape velocity is the minimum speed needed to overcome the gravitational hold of a celestial body and coast away into space without falling back. For a black hole, the concentration of so much mass into such a tiny point creates a gravitational field so intense that this escape speed surpasses the universe's ultimate speed limit. Because nothing can travel faster than light, light itself is forever trapped, unable to carry any visual information about its source to the outside world. Imagine throwing a ball into the air here on Earth. It always falls back. But if you could throw it with incredible force, at over 25,000 miles per hour, it would escape Earth's gravity and never return. A black hole is a place where that required speed is faster than light itself, meaning even the most powerful throw imaginable would be futile. This simple principle reveals that a black hole's darkness is not a color, but a profound statement about the ultimate power of gravity to master even the swiftest and most fundamental force in nature. Since a black hole is inherently invisible, astronomers must become cosmic detectives, searching for clues left behind by these unseen giants. One of the most powerful methods for detecting them is to observe their gravitational influence on nearby stars. In many cases, a black hole is part of a binary system, locked in an orbital dance with a normal visible star. By carefully tracking the star's movement, astronomers can see it wobble, dip, and swing through space as if it were orbiting a massive unseen partner. They can observe a bright, luminous object gracefully circling a patch of complete and total emptiness. From the star's speed and the size of its orbit, scientists can precisely calculate the mass of its invisible companion, and if that mass is great enough, they can confidently conclude that it must be a black hole. It is much like watching a child on a playground swing, flying back and forth through the air. You may not be able to see the person pushing them, but from the rhythm, height, and grace of the child's arc, you can infer the presence and even the strength of the gentle, unseen hand guiding them on their way. While we often picture the singularity at a black hole's heart as an infinitely dense point, for a rotating black hole theory suggests a far stranger reality, a one-dimensional ring. This structure, called a ring singularity, is a consequence of the immense rotational energy inherited from the collapsing star. The powerful centrifugal force generated by the spin works against the relentless inward crush of gravity, preventing the singularity from collapsing into a single zero-dimensional point. Think of a baker tossing and spinning a ball of pizza dough in the air. The rapid rotation flings the dough outward from the center, stretching it into a thin, circular shape with a hole in the middle. In a similar way, the cosmic spin of the black hole is believed to shape its core into an infinitely thin rotating loop. This bizarre structure fundamentally changes the nature of the singularity, transforming it from an inescapable final point into a revolving cosmic threshold of pure theoretical wonder. At the brilliant, blazing centers of some distant galaxies lie the most luminous objects in the universe, quasars and active galactic nuclei. The incredible power source for these celestial beacons is the ferocious activity of a supermassive black hole. In these galactic cores, a black hole is not dormant and quiet, but is actively feeding on an enormous swirling feast of gas, dust, and shredded stars. As this material spirals inward, it forms a vast, superheated accretion disk that radiates an astonishing amount of energy, shining with a brilliance that can outshine all of the billions of stars in its host galaxy combined. Imagine a massive roaring furnace at the heart of a vast dark cathedral. The furnace itself is hidden from view, but the intense light and heat it generates pour out of the cathedral's windows, illuminating the entire surrounding landscape for miles. In the same way, the light we see from a quasar is not from the black hole itself, but is the final brilliant testament to the immense gravitational power it holds over its cosmic domain, a silent engine driving the most spectacular light show in the universe. Beyond the stellar giants and galactic cores, there exists the theoretical possibility of a black hole so small it belongs to the realm of subatomic particles, the micro-black hole. These are purely hypothetical objects for which the strange and wonderful rules of quantum mechanics would become just as important as the immense power of gravity. Unlike their larger cousins, which are described by Einstein's theory of general relativity, a micro-black hole would be so tiny and dense that quantum effects would dominate its existence, blurring the very distinction between a particle and a cosmic object. To date, none have ever been detected, and they remain a tantalizing possibility that lives only within the beautiful landscape of theoretical physics. Imagine a vast, perfectly smooth sheet of silk representing the fabric of space-time. A star is like a heavy bowling ball creating a gentle, wide depression. A micro-black hole, in contrast, would be like a single, microscopic grain of sand, so impossibly dense it pierces a tiny, infinitely deep pucker in the delicate silk. These phantom objects, though unseen, represent one of the greatest frontiers in science, a place where the laws of the very large and the very small must finally meet and tell a single, unified story. If you were to safely watch a friend journey into a black hole from a distance, you would witness one of the strangest sights the universe has to offer. You would never actually see them cross the event horizon. Instead, as they drew closer to that invisible boundary, their movement would appear to slow down dramatically, a consequence of extreme gravitational time dilation. From your perspective, their final moments would be stretched into an eternity. The light from their image would also have to struggle against the immense gravity, losing energy on its journey back to you, causing it to become redder and dimmer, until it faded completely from view. Thanks for watching. It would be like watching a video of a falling object, but as it approaches the ground, the playback speed slows to a crawl, then to a single frame per minute, and finally freezes on the last image, which slowly loses its color and fades to black. Their final moment, for you, would be forever imprinted on the edge of that dark sphere. This reveals a profound truth about the universe. The event horizon is not just a boundary in space, but a boundary in shared experience, where one person's swift final moment becomes another's eternal, fading memory. The birth of a black hole from a dying star can be heralded by one of the most violent and luminous events in the entire universe, a gamma-ray burst. As the core of a truly massive star collapses in on itself to form the singularity, the star's outer layers begin to fall inward at incredible speeds. This chaotic implosion creates a maelstrom of energy, and in some cases, this energy is not trapped, but is instead funneled into two intensely powerful jets of plasma. Blasting outward from the star's poles at nearly the speed of light, these jets tear through the collapsing star's body and erupt into space, carrying with them a focused, blinding torrent of high-energy light. Imagine squeezing a tube of thick paint from the bottom with all your might. All of that pressure is concentrated at the single narrow opening, forcing the paint to shoot out in a straight, powerful stream. In this same way, the star's catastrophic collapse unleashes an immense burst of energy along its axis, a final brilliant act of creation and destruction. It is a profound cosmic paradox that the birth of an object, defined by its perfect, silent darkness, is announced by the universe's most powerful and brilliant scream. The idea of the black hole was not first discovered by a telescope gazing into the night, but was instead born as a ghostly prediction within Albert Einstein's theory of general relativity. His masterpiece reimagined gravity not as a simple pull, but as the deep, graceful curvature of the four-dimensional fabric of space-time. When his complex field equations were solved for a scenario where an immense amount of mass was concentrated in a tiny space, they pointed to a startling and unavoidable outcome. A region of space-time so warped that it would effectively seal itself off from the rest of the universe, creating a hole from which nothing could escape. Imagine an architect designing a revolutionary building using a new set of structural principles. While drawing the blueprints, they might discover that their rules, when followed to their logical conclusion, naturally allow for a room with a door that only opens inward. The black hole was thus a ghost that haunted the elegant machinery of Einstein's new cosmos, a profound indication that reality is governed by laws far more extreme and wondrous than we had ever dared to conceive. If our sun were to be instantly replaced by a black hole of the very same mass, a surprising and profound truth would be revealed. Our Earth would not be pulled in. The gravitational pull of any object, whether it is a star or a black hole, is determined by its mass and your distance from it. From our serene orbit, 93 million miles away, the black hole's gravity would be identical to the Sun's. The Earth, along with every other planet in our solar system, would continue in its familiar, graceful path around that dark, empty point in space, its orbit completely unchanged. Imagine you are swinging a small ball on the end of a long string, circling your hand in a steady orbit. If your hand were to suddenly be replaced by a lead fishing weight of the exact same mass, the ball would not notice the change. It would continue its perfect circular path, held by the same force as before, even though the source of that force has transformed. The true and immediate catastrophe would not be one of gravity, but of a sudden, absolute darkness and a deep, unending cold. In the silent darkness of deep space, two black holes can find each other, locked in a gravitational embrace that will last for eons. As they orbit one another in a final, frantic cosmic ballet, they spiral closer and closer, churning the very fabric of space-time. In the last few moments before they become one, they unleash one of the most powerful events in the entire universe. During this merger, a portion of their mass is converted directly into pure energy, not as light or heat, but in the form of gravitational waves, profound ripples in the fabric of reality itself. In these few seconds, the energy released is greater than the combined light of every star in the entire observable universe. Imagine a master blacksmith forging a new sword, hammering two separate pieces of glowing steel into one. The moment they fuse is marked by a single deafening clang, a shockwave of sound that radiates outward, carrying the energy of the impact. The merger of two black holes is the cosmic equivalent, a silent, universe-shaking event that announces the birth of a new, more massive titan. This reveals that the most silent objects in existence can come together to create the single most powerful event the cosmos has to offer. Surrounding a rotating black hole, just outside its point of no return, is a strange and dynamic region of space known as the ergosphere. This is a place where the black hole's spin is so powerful that it drags the very fabric of space-time along with it, like a spinning ball twisting the threads of a blanket. The rotation is so intense and so swift that within this region, space itself is moving faster than the speed of light. Because of this, it is physically impossible for any object to remain stationary from the perspective of a distant observer. You are not just pulled in, you are forced to move with the current. Imagine stepping onto the edge of a colossal spinning carousel that is moving at an incredible speed. Even if you try to stand perfectly still, the platform beneath your feet will carry you forward. If you tried to run in the opposite direction, you would still be dragged along, unable to escape the ride's relentless motion. The ergosphere is a profound testament to a black hole's power, a domain where it does not just pull matter inward, but commands all motion to follow its silent cosmic spin. Far from being passive agents of destruction, supermassive black holes are active architects in the lives of their host galaxies. They play a crucial role in regulating the rate of star formation, ensuring a galaxy can grow in a balanced and sustainable way over billions of years. As immense amounts of gas and dust are drawn toward the galactic center, the black hole's accretion disk can erupt with incredible energy, launching powerful jets and cosmic winds that travel thousands of light years into space. These outflows act like a gentle cosmic heat wave, warming the vast, cold clouds of interstellar gas that serve as the nurseries for new stars. If this gas becomes too warm, it is too energetic to collapse under its own gravity, effectively pausing star birth in that region and preventing the galaxy from using up all its creative fuel too quickly. Imagine a master gardener tending to a vast celestial garden. They don't just plant seeds, they carefully prune the branches to prevent overgrown chaos, ensuring every part of the garden receives the right amount of light and resources to flourish. In this delicate cosmic dance, the universe's most powerful engine of consumption also acts as its most patient and effective guardian of cosmic resources. The most common type of black hole, the stellar mass black hole, is a cosmic object of a very particular and personal scale, typically weighing between 5 and a few tens of times the mass of our own sun. It is the final, silent remnant of a single, massive star that has exhausted its fuel and collapsed under its own immense gravity. This distinguishes it from its smaller cousins, the neutron stars, and its unfathomably large relatives, the supermassive black holes that anchor entire galaxies. It is the endpoint for a star that was simply too heavy to find a peaceful retirement, its core crushed beyond all known limits of physics into a perfect, quiet darkness. Imagine the difference between a single colossal boulder, so heavy that no force on Earth could ever hope to move it, and an entire mountain range, which is a geological feature of an entirely different order of magnitude. These stellar mass black holes are the solitary boulders of the cosmos, each one a silent, dark monument marking the place where a brilliant, giant sun once blazed in the cosmic night. In the cosmic darkness, some black holes reveal their locations through a brilliant high-energy glow, a signal born from a close and dramatic partnership known as an X-ray binary. In these systems, a stellar mass black hole is paired in a close orbit with a living, luminous star. The black hole's immense gravity acts like a relentless tide, continuously siphoning away streams of gas from the outer layers of its stellar companion. This stolen material does not fall directly into the black hole, but is instead drawn into a swirling, flat whirlpool around it called an accretion disk. Here, the gas is accelerated to incredible speeds, and the intense friction and gravitational pressure heat it to millions of degrees, causing it to radiate not with visible light but with an intense, powerful stream of X-rays. This process is much like a meteor entering Earth's atmosphere. The meteor itself is a cold, dark rock, but as gravity pulls it downward, the friction with the air heats it to a brilliant incandescence, creating a spectacular, fiery trail across the night sky. In an X-ray binary, the stolen stellar gas is a constant stream of fuel, and the accretion disk is a place of cosmic friction that transforms a silent act of consumption into one of the brightest X-ray beacons in the galaxy. The very first image ever captured of a black hole's shadow, that of the supermassive giant in the M87 galaxy, reveals a scale that is almost too vast to comprehend. The dark circular silhouette, which represents the edge of the event horizon, is an astonishing 2.5 times wider than the orbit of Pluto. This means that if this black hole were placed at the center of our solar system, its shadow would extend far beyond the paths of all 8 planets, engulfing the entire realm we call home in a perfect silent darkness. It is an object so large that a beam of light, the fastest thing in the universe, would take several days just to cross from one side of its event horizon to the other. Imagine standing on a perfectly flat plain and seeing a single circular hole in the ground so wide that you could not see the other side, its edge disappearing over the distant horizon. The shadow of the Mate 7 black hole is a cosmic feature of such profound scale, a quiet and humbling reminder that the universe builds its wonders on a canvas far grander than our minds can easily grasp. In one of the most mind-bending and poetic ideas in modern cosmology, some theories suggest that our entire, vast universe might itself exist within the event horizon of a black hole. This concept, known as the black hole cosmology, proposes that the Big Bang, the moment of our universe's creation, could have been the result of a singularity forming in a much larger, higher-dimensional parent universe. In this scenario, the fabric of space-time that makes up our reality is the interior of a black hole, and the expanding nature of our cosmos is a consequence of the strange geometry inside that cosmic boundary. It is like discovering that the beautiful, intricate world painted on the inside of a delicate, hollow sphere is a self-contained reality, unaware of the vast external world in which the sphere itself exists. While this idea remains purely speculative, it is a humbling and beautiful thought, suggesting that the seemingly endless cosmos we see around us could be just a single, perfect seed within an even grander and more mysterious cosmic garden. The size of a black hole's event horizon, a boundary known as the Schwarzschild radius, is governed by a rule of profound and beautiful simplicity. It is directly proportional to its mass. This means that if you were to take a black hole and double its mass by feeding it another star, the diameter of its event horizon would also precisely double. This linear, predictable relationship is a direct consequence of the laws of gravity, a simple mathematical elegance that defines the point of no return. There is no complex formula, no strange exception. The more massive the black hole, the larger its shadow on the universe, in a perfect one-to-one correspondence. Imagine you are filling a simple spherical balloon with water. The amount of water you pour in the mass directly determines the balloon's size. If you pour in 1 liter, it might reach a certain diameter. If you pour in 2 liters, its diameter will be predictably larger. This simple, elegant law provides a calm and orderly measure for the most extreme and chaotic objects in the cosmos, defining the very edge of the abyss with a quiet, mathematical certainty. Black holes are not just a challenge to our imagination, they are a deep and fundamental challenge to our understanding of physics itself. At their core, they create a profound conflict between the 2 great pillars of science, general relativity and quantum mechanics. General relativity is our perfect description of the very large of gravity and the elegant curvature of space-time. Quantum mechanics, on the other hand, is our flawless description of the very small of particles and the strange probabilistic rules they follow. In the singularity of a black hole, these 2 great theories are forced to describe the same reality, and their rules become incompatible. Imagine you have 2 perfect sets of laws. One is the complete and flawless rulebook for how vast oceans behave, describing every current and tide. The other is the perfect rulebook for how continents behave, describing every mountain and grain of sand. But at the very coastline, where the water meets the land, the 2 rulebooks offer contradictory, impossible instructions. This cosmic paradox is a quiet, persistent whisper from the universe, telling us that a deeper, more unified law of nature is still waiting to be discovered. Once you cross the event horizon of a black hole, the very nature of space and time is profoundly and irrevocably warped. Inside this boundary, the inward pull of gravity is so overwhelmingly powerful that it fundamentally alters the geometry of existence. Here, space becomes time-like, and time becomes space-like. This means that the singularity at the center is no longer a physical place you can attempt to avoid. It becomes an inevitable moment in your future, much like next Tuesday is for us. You can no more stop yourself from moving toward the singularity than you can stop yourself from moving toward the next moment in time. Think of it like being in a small boat that has just drifted over the edge of an impossibly vast waterfall. You might be able to steer the boat a little to the left or to the right as you fall, but you cannot change the fact that you are moving in only one direction, down. The singularity is the ultimate down for the universe, a future that is as certain and as unavoidable as the relentless forward flow of time itself. While we often think of supermassive black holes as stationary anchors at the hearts of their galaxies, they can sometimes be torn from their cosmic homes to become silent, solitary wanderers. This profound ejection can occur during the chaotic and beautiful process of a galactic merger. As 2 galaxies collide and their central supermassive black holes begin a long, spiraling dance toward each other, their combined gravitational influence creates an immensely powerful and unstable environment. If another massive object, such as a 3rd black hole or a dense star cluster, is caught in this violent waltz, it can be subjected to a tremendous gravitational slingshot, flinging it out of the newly formed galaxy at incredible speeds. Imagine a game of cosmic billiards, where 2 massive spinning balls spiral toward the center pocket. If a smaller ball happens to roll between them at just the right moment, the immense energy of their interaction can launch it clear off the table, sending it flying into the vast, surrounding emptiness. This means the silent, dark void between the galaxies may not be as empty as it seems, but could be quietly populated by countless lost, invisible titans, each a gravitational ghost on an endless journey through the cosmic night. The creation of a black hole is a testament to gravity's ultimate and final victory over all other forces in the universe. Inside the core of a dying, massive star, the pressure becomes so mind-bendingly immense that it overcomes even the most powerful repulsive forces known to physics. First, it crushes the atoms themselves, forcing the electrons into the protons to create a dense ball of neutrons. But in a star that is massive enough, even the powerful quantum force that keeps these neutrons from occupying the same space, a principle called neutron degeneracy pressure, is not enough. Gravity's relentless inward crush shatters this final defense, and the matter of the core collapses without end. It is much like a building with a series of fail-safes designed to prevent its collapse. The main supports might buckle, but a secondary system catches the load. Then, that system fails, but a final, powerful emergency brake engages. The formation of a black hole is what happens when the weight is so immense that the single one of these protections, from the strongest to the most fundamental, fails in a cascading, unstoppable sequence, leaving nothing to oppose the final, silent descent into a singularity. Just as seismologists study the vibrations of the Earth to understand its hidden interior, physicists have developed a field called black hole seismology to probe the fundamental nature of these cosmic objects. When a black hole is disturbed, either by consuming a star or by merging with another black hole, its event horizon can ripple and vibrate, much like the surface of a bell that has just been struck. These vibrations, known as quasi-normal modes, are not random. They are a clear, predictable ringing that quickly fades as the black hole settles back into a perfect, stable sphere. The precise frequencies and damping times of this ring down are determined solely by the black hole's mass and spin, providing a direct and powerful way to test the predictions of Einstein's theory of general relativity in the most extreme gravitational environment imaginable. It is like listening to the pure fading tone of a tuning fork in a silent room. From the exact pitch and the duration of its hum, you can learn everything there is to know about the tuning fork's physical properties without ever needing to see or touch it. This gentle cosmic ringing is the unique and beautiful song of space-time itself, a quiet and profound echo of its most violent and transformative moments. A spinning black hole is not just an endpoint for energy, but a potential source of it through a remarkable theoretical method known as the Penrose process. This ingenious idea makes use of the ergosphere, the region outside the event horizon, where the black hole's rotation drags space-time along with it. A projectile could be sent into this swirling region and designed to split into two pieces. If timed perfectly, one piece would fall past the event horizon, while the other would be powerfully ejected, flying out with significantly more energy than the original object possessed. This extra energy is not created from nothing, it is stolen directly from the black hole's immense rotational momentum, causing its spin to slow down by an infinitesimal amount. Imagine a child on a fast-spinning carousel who throws a heavy ball backward against the direction of the spin. This action would give the child a small push forward, slightly boosting their own speed, while the thrown ball slows the carousel's rotation by a tiny, almost immeasurable amount. It reveals that even in the most inescapable places, the universe has hidden away vast reservoirs of energy, waiting for a clever enough mind to imagine how to set them free. Unlike a planet or a star, a black hole does not possess a solid surface that you could ever hope to touch or stand upon. The boundary that we perceive as its edge, the event horizon, is not a physical barrier or a tangible membrane, but rather a profound and invisible threshold in the very geometry of space-time. Crossing it is not an act of collision, but an act of passage. Once you drift past this point of no return, your journey is not halted. it simply becomes a one-way trip toward the central singularity, with nothing but the warped fabric of reality to guide you. Imagine the horizon you see across a vast, calm ocean. It appears as a distinct and definite line, the place where the water meets the sky. Yet, if you were to sail toward it, you would find that it is not a physical destination you can ever reach. It is a boundary of perception that recedes as you approach. The event horizon of a black hole is a boundary of causality, just as intangible, but infinitely more absolute, a silent edge that marks the end of the observable universe. The immense gravitational authority of Sagittarius A star, the supermassive black hole at the heart of our Milky Way, is most beautifully demonstrated by the stars that live in its immediate neighborhood. These stars, known as stars, are locked in incredibly tight and rapid orbits around the galactic center, moving at speeds that are truly mind-boggling. Some of them have been observed hurtling through space at several million miles per hour, completing their celestial laps in just a few years, a stark contrast to our own sun's serene 230 million year journey around the same point. Their frantic, precise paths are like a celestial time-lapse, allowing astronomers to trace their orbits and, in doing so, to precisely map the gravitational field and confirm the mass of the silent, invisible object they are all faithfully circling. It is much like watching a group of tetherballs swinging in tight, perfect circles around a central, unseen pole on a windy day. The faster they whip around, and the smaller their circles, the more you understand about the immense strength and stability of the anchor that holds them all so securely in their frantic cosmic dance. The brilliant, almost blinding light that emanates from the vicinity of a black hole does not come from the black hole itself, but from the incredible violence of matter's final, desperate spiral. The light we see is generated by the accretion disk, a swirling carousel of gas, dust, and stellar debris. As this material is pulled inward, the particles are compressed and accelerated, creating an immense amount of friction and heat. This cosmic rubbing of matter against matter causes the disk to blaze at millions of degrees, radiating an astonishing amount of energy in the form of X-rays and other forms of light. This is very much like the way a meteor becomes a brilliant shooting star. The cold, dark rock from space does not itself begin to shine. Instead, it is the intense friction created as it plows through the Earth's atmosphere that heats the surrounding air to a state of glowing incandescence. The light from a black hole's domain is therefore a kind of cosmic farewell, a final, brilliant scream from matter as it is heated to oblivion just before it crosses the threshold of silence forever. While black holes are not eternal, their lifespan is so incomprehensibly long that they are among the most permanent objects in existence. A supermassive black hole, one with the mass of 1 billion suns, would take longer than the current age of the universe to completely disappear through the faint whisper of Hawking radiation. This is because the rate of this quantum evaporation is inversely proportional to the black hole's mass. The larger a black hole is, the colder its temperature, and the more slowly it radiates its energy away into the cosmos. While a tiny, hypothetical black hole might vanish in a brilliant flash of energy, its colossal relatives fade with a slowness that defies all human scales of time. Imagine the difference between a single delicate snowflake melting on a warm sidewalk and a colossal iceberg miles wide, slowly sublimating under the faint warmth of distant starlight. The snowflake is gone in a moment, while the iceberg will endure for an age, its immense size making it almost impervious to such a gentle process. In this way, the universe's largest black holes are the ultimate monuments to endurance, destined to outlive the very stars and galaxies that surround them. Reigning over a dark and silent cosmos for an almost infinite time, the closest supermassive black hole to our world is the very same one that serves as the quiet gravitational heart of our own Milky Way galaxy. This gentle giant, known as Sagittarius A star, lies approximately 26,000 light-years away, nestled safely at the center of our spiraling cosmic home. To put this immense distance into perspective, A single light year is the distance that light travels in a year, which is nearly 6 trillion miles. So, the light that we might one day see from the stars orbiting this black hole began its journey toward Earth around the time that the first modern humans were beginning to paint stories on the walls of ancient caves. It is a distance of profound and comforting scale, placing us far from the chaotic and brilliant activity of the galactic core. It is like living in a peaceful, quiet suburb on the very outskirts of a vast and bustling city. You know that the city's vibrant, powerful center is there, the engine that drives everything around you, but you are far enough away to appreciate its existence from a serene and beautiful distance, content to be part of its calm, gentle, and slow-moving rhythm. While we can never hope to see a black hole directly, we can witness its unmistakable presence through the profound and beautiful way it distorts the light traveling around it. This effect, known as gravitational lensing, occurs because a black hole's immense mass creates such a deep and powerful well in the fabric of space-time that it bends the path of any light that happens to pass nearby. As light from a distant star or galaxy travels close to the black hole on its long journey to us, its path is warped and redirected, creating distorted, magnified, or even multiple ghostly images of the background object from our point of view on Earth. It is much like looking at a smooth grey stone resting at the bottom of a perfectly clear flowing creek. You cannot see the invisible current of the water itself, but you can see its undeniable effect in the way the stone's image appears to shimmer, bend, and magnify, its shape constantly being altered by the gentle lens of the moving water passing over it. In this beautiful paradox, the universe uses the light from the most distant stars to draw a perfect map of the places where light cannot go. Before the universe knew the name black hole, the concept of such an object flickered in the minds of early physicists under the elegant title of a dark star. In the late 18th century, the French mathematician Pierre-Simon Laplace, building on the work of John Michel, used the principles of Newtonian gravity to imagine a star of immense density. He reasoned that if light were made of particles, as was commonly believed, a star could be so massive and compact that its escape velocity would exceed the speed of light itself. Any light emitted from its surface would be caught in an unbreakable gravitational grip, rising only to fall back down, rendering the star utterly invisible to the cosmos. This early concept was like the first charcoal sketch of a grand masterpiece. It was a simple outline, drawn with the tools of classical physics, yet it perfectly captured the essential, haunting shadow of the far more complex and profound object that Einstein's theories would one day fully reveal. It is a profound testament to the power of human curiosity that the ghost of a black hole was first seen not through a telescope, but through the pure, quiet force of logical thought. A black hole can spin at a speed that is almost incomprehensibly fast, approaching the absolute speed limit of the universe itself. When a massive star, which is already rotating, collapses under its own gravity, its spin is conserved and dramatically amplified, much like an ice skater who pulls their arms in to spin faster. This can result in a black hole whose event horizon is whipping around at a velocity that is close to the speed of light. This incredible rotation doesn't just happen in a vacuum. It profoundly shapes the very fabric of space-time around it, dragging it along in a powerful cosmic whirlpool. Imagine a vast spinning top, so perfectly balanced and so incredibly fast that its surface is a blur, its motion almost a perfect silent hum. The black hole is the universe's ultimate spinning top, an object of immense mass and energy, whose rotation is so extreme it bends the very rules of space and time to its will, a quiet and powerful testament to the enduring power of cosmic momentum, a profound and yet unproven idea in the physics of black holes, is the cosmic censorship hypothesis. This principle suggests that the singularity at the heart of a black hole must always be clothed by an event horizon, forever hidden from the view of the outside universe. It proposes that nature forbids the existence of a naked singularity, a singularity that would be visible and could therefore causally affect the rest of the cosmos. If a naked singularity were to exist, it would be a place where the laws of physics break down in a way that is observable, a point of infinite density and infinite chaos, spewing unpredictable information into our reality. The cosmic censorship hypothesis is like a fundamental law of cosmic decency, suggesting that the universe will always shield its most extreme and unpredictable infinities behind a veil of perfect, causal modesty. It is a comforting and elegant idea, a belief that the ultimate secrets of the universe's creation and destruction are meant to be kept as just that, secrets, forever locked away behind a silent one-way door. The very first black hole to be confidently identified, the pioneering discovery known as Cygnus X1, is a stellar mass black hole of truly impressive proportions. By carefully studying the graceful, consistent orbit of its companion, a brilliant blue supergiant star, astronomers have been able to measure its mass with remarkable precision. It is now understood to weigh approximately 21 times the mass of our own Sun, all of which is condensed into a sphere with an event horizon only about 77 miles across. This makes it one of the more massive stellar mass black holes known in our galaxy, an object that was born from the collapse of a truly colossal star that lived its life in a brilliant, fiery blaze. Imagine a single, perfectly smooth cannonball, so dense that it weighs more than a fleet of 100 massive cruise ships combined. Cygnus X1 is the cosmic equivalent, a silent, dark sphere of unimaginable density, its quiet presence a constant and powerful reminder of the giants that once roamed the starfields of our galactic home. From the chaotic, brilliant heart of some supermassive black holes, twin jets of superheated plasma are launched into the cosmos at nearly the speed of light. These are not small, fleeting bursts of energy, but are instead colossal, focused beams that can extend for hundreds of thousands of light years, stretching far beyond the visible boundaries of their own host galaxy. They are formed from the immense magnetic and rotational forces within the accretion disk, which act as a cosmic particle accelerator, funneling matter and energy outward in two perfectly opposing streams. Once launched, these jets travel with such power and precision that they can plow through the thin, intergalactic medium, heating gas, and influencing the very evolution of the cosmic structures around them. It is as if a colossal, invisible lighthouse were standing at the center of a vast, dark ocean, sending out two perfectly straight, unwavering beams of light that travel not for miles, but for distances that span the cosmic sea itself. These jets are a profound testament to a black hole's power, showing that it does not just consume, but can also create the largest and most energetic structures in the entire universe. Not all black holes are bound to the familiar graceful orbits of a galaxy. Some are solitary wanderers, cosmic nomads that travel through the vast, dark emptiness of intergalactic space. These rogue or nomad black holes are thought to have been ejected from their home galaxies through powerful gravitational interactions, most likely during the chaotic and violent merger of two galaxies. In these cosmic collisions, the delicate dance of stars and black holes can be profoundly disturbed, and a smaller black hole can be caught in a gravitational slingshot, flinging it out into the void at incredible speeds. Imagine a quiet, peaceful village nestled in a calm valley. One day, a powerful earthquake reshapes the entire landscape, and in the chaos, a single, heavy stone from the village's foundation is dislodged and sent rolling out into the vast, empty plains beyond. These silent, invisible travelers are the cosmic equivalent, each one a lost heart of a star or a galactic core, now on an endless, lonely journey through the silent, starless dark. If you could somehow take our entire planet Earth and compress it down until it became a black hole, the resulting object would be no larger than a small glass marble. Every mountain, every ocean, the deep iron core, and the very air we breathe would need to be crushed down beyond the limits of matter itself. This is because to become a black hole, An object's entire mass must be squeezed into a space so small that its own gravity becomes inescapable. For the Earth, this critical size is astonishingly tiny, less than an inch in diameter. Think of taking a vast, sprawling forest with every tall tree, every hidden animal, and every single leaf, and compressing all of it down until it fits into a single, tiny acorn. All the substance of our world, reduced to something you could hold in the palm of your hand. This profound transformation reveals that the solid world we stand upon is almost entirely empty space, a delicate arrangement of atoms that gravity, in its ultimate expression, can effortlessly sweep aside. The union of two black holes does not always end in quiet stillness. In a phenomenon known as a merger recoil, the newly formed larger black hole can be violently kicked, sent speeding off on a new trajectory through the cosmos. This powerful shove is a direct consequence of the immense blast of gravitational waves released during the merger. If these waves are not radiated with perfect symmetry in all directions, they create a net thrust, pushing the new black hole the other way. It is much like the recoil of a powerful rocket engine. As the engine blasts a tremendous the amount of energy and exhaust downward, the rocket itself is propelled with equal and opposite force upward. The asymmetrical storm of gravitational waves acts as a celestial engine, giving the new black hole a sudden and powerful push. This cosmic kick reveals that even the most massive and seemingly immovable objects in the universe are subject to the violent and unpredictable choreography of their own creation. Within the already mysterious depths of a rotating black hole, theory predicts the existence of a second, even more enigmatic boundary known as the inner horizon. This is a purely mathematical concept that lies beyond the familiar event horizon, a final threshold before one would reach the ring singularity at the very heart of the black hole. At this strange second frontier, the bizarre effects of the singularity are theorized to begin to manifest in truly mind-bending ways. Some solutions to Einstein's equations suggest that time and space might become so warped here that it could be a gateway to other universes, or a point where the deterministic laws of causality finally break down. Imagine a journey into a deep, dark, and unexplored cave. The mouth of the cave is the first threshold, a clear point of entry. But deep inside, you might find a second, narrower passage, a final, tight squeeze that leads to a part of the cave that is fundamentally different and operates under an entirely new set of rules. The inner horizon is this final, theoretical gateway into the deepest and most profound mysteries of space-time. Supermassive black holes, the cosmic titans that anchor entire galaxies, did not spring into existence fully formed. They likely began their lives as much smaller black holes in the early universe, growing to their immense sizes over billions of years through a patient and relentless process of consumption and mergers. In the dense, chaotic environment of a young galaxy, these black hole seeds would have fed on the abundant supply of surrounding gas and dust, steadily increasing their mass. Their greatest growth, however, would have come from the dramatic and violent collisions with other black holes. As galaxies merged, their central black holes would eventually find each other, spiraling inward to combine into a single, even more massive object. It is a process of cosmic consolidation, much like a single tiny raindrop on a vast window pane. At first, it is small and insignificant, but as it slowly slides down the glass, it joins with other raindrops along the way, growing larger and more substantial with each and every quiet merger, until it becomes a powerful, flowing stream. To detect the faintest and most profound whispers from the cosmos, humanity has built extraordinary observatories, like LIGO and Virgo, that are not designed to see, but to listen. These facilities are built to sense the infinitesimal ripples in space-time known as gravitational waves, the final echoes of the universe's most violent and dramatic events. Each observatory consists of two long perpendicular tunnels, forming a giant L shape. A laser beam is split and sent down each of these arms, where it bounces off a mirror and returns to a detector. If a gravitational wave, created by the merger of two black holes or the collision of neutron stars, passes through the Earth, it will stretch and squeeze the very fabric of space-time itself. This minute distortion will cause the length of one of the tunnels to change by a distance smaller than the width of a proton, a change so incredibly tiny that the sensitive laser instruments can detect it. It is like a cosmic spider, sitting at the center of a vast, silent web. It cannot see the distant edges of its creation, but if a single tiny fly were to land on a faraway thread, the spider would instantly feel the faint telltale vibration. The brilliant, swirling colors of a black hole's accretion disk are not just a beautiful cosmic spectacle, they are a direct and precise measure of its incredible heat. As gas and dust are pulled into a relentless spiraling descent, the intense friction and compression heat the material to millions of degrees Celsius. The inner regions of the disk, closest to the event horizon, are the hottest and most energetic, glowing with the high-energy light of X-rays. The outer regions, which are cooler, radiate in lower energy forms like ultraviolet or even visible light. By studying this spectrum of cosmic colors, astronomers can map the temperature of the disk with remarkable accuracy, reading its thermal structure from afar. It is very much like watching a blacksmith heat a piece of iron in a forge. The iron first begins to glow a dull, deep red, then a fiery orange, and as it gets hotter still, it shines with a brilliant white-hot light. By simply observing the color of the glowing metal, the blacksmith knows its temperature and is ready to shape it. In the same way, the beautiful and violent dance of color around a black hole provides a perfect cosmic thermometer, allowing us to measure the staggering heat of matter's final moments. A black hole is not a bizarre cosmic accident or a strange unnatural anomaly. It is, in fact, a natural and inevitable consequence of gravity, as described by Einstein's theories. His equations show that gravity is the curvature of space-time caused by mass, and that if you concentrate enough mass into a small enough volume, the curvature will become so extreme that it effectively seals itself off from the rest of the universe. There is a point of no return, a density beyond which no known force in nature can stop the final, complete gravitational collapse. The formation of a black hole is not a matter of if, but when, once this critical threshold is crossed. Imagine stacking heavy books, one by one, onto a thin wooden plank suspended between two chairs. At first, the plank sags and bends, but it holds. But there is a definite, specific number of books that will inevitably cause the plank to snap. The black hole is the universe's ultimate breaking point, a quiet and profound statement that even the fabric of reality itself has its limits, and that gravity, given enough power, is the force that will always in the end prevail. The gravitational forces in the immediate vicinity of a black hole are so incredibly extreme that they can alter the very fabric of space and time in the most profound and fundamental ways. This is the core prediction of Einstein's theory of general relativity, which tells us that gravity is not a force that acts within space, but is instead a property of space-time itself. A black hole's immense mass creates a deep, steep well in this four-dimensional fabric, and the closer you get to it, the more warped and distorted the geometry of reality becomes. It is a place where the familiar, straight lines of Euclidean geometry become gracefully curved paths, where the steady universal tick of a clock slows to a near standstill, and where the one-way direction of time can become a one-way direction in space. It is like taking a flat, perfectly stretched rubber sheet and placing a heavy bowling ball in its center. The sheet is no longer flat. It is now a landscape of deep, flowing curves, where the straightest path is no longer a straight line, but a graceful, spiraling arc. A black hole is the ultimate expression of this cosmic curvature, a place where gravity is not just a force, but is the absolute and undisputed master of reality itself. Though a black hole is fundamentally invisible, its commanding presence can be inferred from the brilliant high-energy light that is produced when it interacts with the matter in its cosmic neighborhood. A dormant, isolated black hole wandering silently through the void is nearly impossible to detect. But when a black hole is part of a binary system with a star, or when it resides at the crowded center of a galaxy, its immense gravity can pull in vast amounts of surrounding gas and dust. As this material spirals inward, it forms a superheated accretion disk that glows with an incredible luminous intensity, radiating vast quantities of X-rays and other forms of high-energy light. It is much like a silent, invisible ship sailing on a vast, dark ocean at night. You cannot see the ship itself, but you can clearly see the brilliant phosphorescent wake it leaves in the water, the glowing trail of disturbed, agitated plankton that perfectly outlines the path of the unseen vessel. In this same way, the universe uses the final brilliant scream of consuming matter to illuminate the perfect, silent darkness of its most profound and mysterious creations. Black holes, despite their reputation as eternal cosmic prisons, are not forever. According to the groundbreaking theories of Stephen Hawking, they are predicted to have a finite lifespan, slowly and gracefully evaporating over truly astronomical timescales. This gradual demise is a result of a quantum mechanical process known as Hawking radiation, where the black hole loses an infinitesimal amount of its mass energy by emitting a faint thermal glow from its event horizon. For a stellar mass black hole, this process is so incredibly slow that it would take far longer than the current age of the universe for it to completely disappear. For a supermassive black hole, the timescale is even more vast, bordering on the unimaginable. It is like watching a colossal mountain, made of the hardest granite, being slowly eroded by the gentle, persistent whisper of a soft and steady wind. While the wind's effect is imperceptible in any human lifetime, given an eternity, it will inevitably wear the entire mountain down to a flat and silent plain. This beautiful, slow decay reveals a profound cosmic truth, that in the grand, patient arc of the universe, nothing, not even the embodiment of perfect darkness and permanence, is truly eternal. The study of black holes is far more than an exploration of strange and distant cosmic objects. It is a profound and essential test of the very limits of our most fundamental theories about the universe. Black holes are the natural laboratories of the cosmos, places where the forces of gravity and the nature of space-time are pushed to their absolute extremes, far beyond anything we could ever hope to replicate here on Earth. By observing the way that light bends around them, by listening to the gravitational waves created when they merge, and by wrestling with the deep paradoxes they create, scientists are able to probe the intricate and beautiful predictions of Einstein's theory of general relativity with unprecedented accuracy. It is like a master shipbuilder who wants to test the absolute strength of a new hull design. They can perform all the calculations they want on paper, but the true test only comes when the ship is launched into the most powerful and violent storm imaginable. Black holes are that perfect cosmic storm, a place where our most elegant ideas are forced to confront the beautiful and unforgiving reality of the universe. In 2015, humanity's perception of the cosmos was forever changed. For the very first time, we directly detected gravitational waves, the faint cosmic ripples in the fabric of space-time that were predicted by Albert Einstein a century earlier. This historic Nobel Prize-winning discovery was made by the LIGO Observatory, and the signal it received was the unmistakable signature of two stellar mass black holes, each about 30 times the mass of our Sun, spiraling into each other and merging in a distant galaxy over 1 billion years ago. The faint chirp that the detectors heard was the sound of the final, frantic moments of this cosmic dance, a beautiful and powerful confirmation that black holes not only exist, but that they can come together in one of the most violent and energetic events the universe has to offer. It was as if, after a lifetime of only watching to the life, seeing still photographs of the ocean, we were suddenly able to hear the profound and unmistakable sound of two colossal waves crashing together on a distant, unseen shore. This single, quiet moment of listening opened up an entirely new way to experience the universe, a new sense with which to explore the silent, dark symphony of the cosmos. When a star more than 20 times the mass of our Sun finally exhausts its nuclear fuel, its final moments are governed by a single inexorable force: gravity. In that instant, there is no known physical force in the entire universe that can halt the catastrophic collapse of its core. The immense pressure overwhelms the powerful quantum mechanical principles that keep neutrons from occupying the same space, a final line of defense known as neutron degeneracy pressure. Once this last bastion is breached, the collapse is absolute and unstoppable, continuing until all the matter of the star's core has been crushed into a singularity of infinite density. Imagine a series of immensely strong reinforced walls, each one designed to hold back an unimaginable weight. The formation of a black hole is what happens when the weight becomes so great that it doesn't just break the first wall, but shatters every single wall in a single, instantaneous, and cascading failure, leaving nothing but an open path to the very end. This reveals gravity's ultimate and final authority in the cosmos, a patient and silent force that, given enough mass, will always win the final cosmic battle. The term singularity, used to describe the very heart of a black hole, is more than just a name for a physical object. It is a profound and honest admission of the limits of our own knowledge. A singularity is, by its very definition, a point where our current laws of physics, the elegant and powerful equations of general relativity, cease to provide a meaningful description of reality. As you approach this point of infinite density and zero volume, the mathematical values that describe the curvature of space-time spiral up toward infinity, and the familiar, predictable rules of the cosmos simply break down. It is the physical embodiment of a mathematical paradox, a place where our understanding comes to a respectful and silent halt. It is like a brilliant and ancient map of the world, drawn with incredible precision and detail, showing every river, mountain, and coastline. But at the very center of the map, the cartographer has simply written, "Here be dragons." The singularity is that final uncharted territory, a quiet and humbling reminder that beyond the edge of our known world, the universe still holds its deepest and most profound mysteries. The powerful jets of plasma that are launched from the accretion disks of supermassive black holes can have a profound and dualistic effect on their host galaxies, acting as both creators and destroyers of stars. In some instances, these immensely powerful outflows can trigger a beautiful cascade of new star formation. As the jets plow through the vast cold clouds of interstellar gas, they can create shockwaves that compress the gas, providing the necessary spark to initiate its gravitational collapse into dense, new stellar nurseries. In other cases, however, these same jets can effectively halt star formation. If the energy they inject into the gas clouds is too great, it can heat the gas to a point where it becomes too diffuse and energetic to collapse, effectively sterilizing the region and preventing new stars from being born. It is a delicate cosmic balance, much like the role of a great river in shaping a vast and fertile floodplain. In a gentle, steady flow, the river can deposit rich, life-giving silt, encouraging new growth. But in a powerful, violent flood, it can sweep away the very soil it once nurtured, leaving behind a barren and empty landscape. To exist within a black hole's photon sphere, the ethereal region where light itself can be trapped in, orbit, would require an object to travel at a speed that is almost beyond comprehension. An object with mass would need to be moving at a velocity greater than 99.9% of the speed of light, just to maintain a stable circular path in this incredibly warped region of space-time. Any slower, and it would be pulled into a decaying spiral, eventually crossing the event horizon. Any faster, and it would break free from its gravitational prison, flung out into the relative safety of the wider cosmos. This is the ultimate cosmic balancing act, a celestial knife's edge where the slightest deviation in speed means the difference between escape and eternal capture. It is like trying to balance a spinning top on the very tip of a perfectly sharp needle. The slightest wobble, the faintest breeze, and the delicate equilibrium is lost. The photon sphere is the universe's most perfect and most precarious expression of this beautiful, fleeting balance. While we can only see a handful of black holes, their true population in our home galaxy is thought to be vastly greater than we can currently detect. Based on the number of massive stars that have lived and died over the Milky Way's long history, astronomers estimate that there could be as many as 1 billion stellar mass black holes silently and invisibly drifting through the cosmic darkness. The vast majority of these are thought to be dormant and isolated, not part of a binary system and not actively feeding on any nearby gas or dust. This makes them almost impossible to find with our current technology, as they emit no light and have no obvious gravitational dance partner to give away their secret location. Imagine walking through a vast, dark forest at midnight. You might only be able to see the few fireflies that happen to be glowing in your immediate vicinity, but you know, with a quiet certainty, that for every one you see, there are thousands, perhaps millions, of other, silent insects hidden in the power, surrounding darkness. In this same way, the black holes we have found are just the first, faint glimmers of a vast and hidden population of silent, celestial ghosts. The environment in the immediate vicinity of a supermassive black hole is one of the most extreme and violent places in the entire universe. It is a region of profound and chaotic contrasts, a place of both blinding light and perfect darkness. Here, entire stars are torn apart by immense tidal forces, their gas pulled into a swirling superheated accretion disk that glows with the light of 1 trillion suns. From this brilliant chaotic furnace, powerful magnetic fields launch twin jets of plasma that travel at nearly the speed of light, stretching for hundreds of thousands of light years into the silent intergalactic void. At the very center of this maelstrom of energy and destruction sits a region of perfect, calm silence, the event horizon, a one-way door into a place of infinite gravity and unimaginable mystery. It is like the serene, quiet eye of a colossal world-spanning hurricane. All around is the violent, roaring chaos of the storm, but at its very heart is a place of absolute and deceptive tranquility. This cosmic paradox reveals the profound and beautiful duality that lies at the heart of our universe, a place where the most extreme violence and the most perfect peace can exist, side by side. In the asymmetric and beautiful world of theoretical physics, some ideas have proposed that black holes could be one end of a cosmic tunnel known as a wormhole, or an Einstein-Rosen bridge. This speculative concept suggests that the singularity at the heart of a black hole might not be an endpoint, but a gateway, a theoretical shortcut through the very fabric of space-time that could connect two vastly distant points in our universe, or even connect our universe to another one entirely. In this tantalizing vision, a black hole would be the entrance to this cosmic passage, while its hypothetical and elusive twin, a white hole, would be the exit. Imagine folding a vast two-dimensional map in half, so that two distant cities are now touching. If you were to then push a needle through both layers of the paper, you would create a tiny instantaneous bridge between them, a path far shorter than the long winding roads on the map's surface. While there is no experimental evidence to suggest that wormholes are real, they remain a beautiful and profound possibility, a testament to the quiet, imaginative power of a mind at play in the silent fields of cosmic theory. The density of the matter that is crushed into the singularity at the heart of a black hole is thought to be, for all practical purposes, infinite. This is a concept that challenges the very limits of our physical intuition, as it describes a state where a finite, and often immense, amount of mass is concentrated into a region of zero physical volume. According to the mathematics of general relativity, the gravitational collapse of a star's core continues without any known force to stop it, resulting in a point of literally infinite density and infinite space-time curvature. It is a place where our familiar notions of space and matter simply cease to have any meaning. Imagine taking a single heavy grain of sand and placing it on a perfectly flat, infinitely large rubber sheet. Now, imagine that this single grain of sand has the mass of an entire mountain. The sheet would be stretched downward so steeply and so profoundly that it would effectively create an infinitely deep and narrow well. The singularity is the universe's ultimate expression of this impossible concentration, a place where the familiar, gentle laws of nature are pushed to their absolute and final breaking point. Observing the shadow of a black hole, that dark silhouette against the brilliant glow of its accretion disk, requires a level of observational power that is truly astronomical. To achieve the necessary resolution to see such a small and distant object, astronomers needed to create a virtual telescope with a mirror the size of the entire Earth. This remarkable feat was accomplished by the Event Horizon Telescope, a global network of radio telescopes scattered across the planet from the mountains of Chile to the frozen landscapes of Antarctica. By perfectly synchronizing these individual observatories, using atomic clocks of incredible precision, and then combining their collected data, scientists were able to create a single, Earth-sized virtual dish, a technique known as very long baseline interferometry. It is like having 1,000 individual musicians in 1,000 different cities all play a single, perfect note at the exact same time. While each individual sound might be faint, when they are all combined in perfect harmony, they can create a powerful and resonant chord that can be heard across the world. This beautiful act of global scientific cooperation allowed us, for the very first time, to see the quiet and profound shape of the abyss. From a safe and respectful distance, a black hole's gravity is no more mysterious or powerful than that of any other celestial object of the same mass. Its gravitational influence follows the same inverse square law that governs the graceful orbits of the planets in our own solar system. If you were to replace our Sun with a black hole of the exact same mass, the Earth's orbit would not change in the slightest. We would simply be plunged into a deep and profound darkness. The true and unique danger of a black hole only manifests itself when you get very, very close to it. It is much like the difference between a calm, gentle river and a towering, powerful waterfall. From miles away, the river is just a serene and predictable body of water. But as you draw closer, you begin to feel the inexorable pull of the current, a force that becomes exponentially more powerful until you reach the final, inescapable precipice. A black hole's. The reputation for cosmic terror is a matter not of its reach, but of its profound and absolute finality. A quiet and gentle giant that only reveals its true and terrible strength at the very end of the journey. When a star ventures too close to a supermassive black hole, its demise is announced across the cosmos by a brilliant and fleeting flash of light known as a tidal disruption flare. This spectacular event occurs as the star is violently torn apart by the black hole's immense tidal forces, a process that stretches and shreds the star into long, flowing streams of superheated gas. As this stellar debris is captured by the black hole's gravity, it swirls into a temporary brilliant accretion disk, a final, chaotic blaze of glory before it is consumed. This sudden, intense burst of radiation can be detected by telescopes across the universe, a unique and unmistakable signature of a star's final, violent moments. It is like a single brilliant firework exploding in a vast, dark, and silent night sky. For a brief and beautiful moment, it illuminates everything around it with a spectacular cascading shower of light, and then, just as quickly, it fades back into the quiet and perfect darkness, leaving only the memory of its brief and fiery existence. The reason that nothing, not even light, can escape from the gravitational pull of a black hole is rooted in one of the most fundamental and absolute laws of our universe, that nothing can travel faster than the speed of light in a vacuum. A black hole's gravity is so immensely powerful that, at its event horizon, the escape velocity required to break free from its grip is greater than this cosmic speed limit. Since nothing in the universe can achieve this impossible speed, everything that crosses the event horizon is forever trapped, its journey now having only one possible direction: inward. It is like a runner trying to escape a country where the only law is that you cannot run faster than 10 miles per hour, but the border is at the top of a hill that requires a speed of 11 miles per hour to climb. No matter how fast the runner is, the hill represents a physical and absolute impossibility. The event horizon is the universe's ultimate and most profound hill, a quiet and gentle slope that not even the swiftest and most fundamental force in nature can ever hope to climb. While the mass of a black hole can be billions of times that of our Sun, the size of the singularity at its heart is thought to be infinitesimally small. According to the classical theory of general relativity, the singularity is a one-dimensional point in space for a non-rotating black hole and a one-dimensional ring for a rotating one. This means it has zero volume, a place where a colossal amount of matter has been crushed down to a size that is smaller than a single subatomic particle, smaller than a quark, smaller than anything we can physically measure or even truly comprehend. It is a place where our familiar notions of size and distance simply cease to exist. Imagine taking the entire vast and sprawling Library of Congress, with all of its millions of books, maps and photographs, and storing all of that information not on a tiny microchip, but on a single, perfect, and indivisible letter A on a single page. The singularity is the universe's ultimate act of cosmic compression, a place where all the beautiful and complex reality of a star is reduced to a single, perfect point of infinite and beautiful silence. The discovery of incredibly massive, supermassive black holes in the very early universe presents a profound and beautiful challenge to our current models of how these cosmic giants grow. These ancient quasars, seen at a time when the universe was less than 1 billion years old, are already billions of times the mass of our Sun. This suggests that they must have grown to their immense sizes incredibly quickly, far faster than our theories of gradual gas consumption and stellar mergers would comfortably allow. It is like finding a towering ancient redwood tree that is thousands of years old, but in a forest that you know for a fact is only 100 years old. Its very existence is a beautiful and quiet paradox, a gentle hint from the universe that there is something profound and fundamental about its early life that we have not yet come to understand. These impossibly large, impossibly young black holes are one of the great and gentle mysteries of modern cosmology, a silent and beautiful puzzle that whispers to us from the very dawn of time. A black hole with the mass of Mount Everest, the tallest and most majestic mountain on our planet, would be an object of truly mind-bending proportions. Its event horizon, the point of no return, would be smaller than a single atom. This is a direct consequence of the incredibly dense nature of black holes, where an immense amount of mass is concentrated into an almost impossibly small space. To create such an object, you would need to take every single rock, every flake of snow, and every ounce of that colossal mountain's being, and crush it down into a region of space that is far smaller than the wavelength of visible light. Imagine taking a vast, sprawling city, with all of its towering skyscrapers, bustling streets, and millions of people, and compressing all of it down until it fits into a single, tiny grain of sand. This beautiful and profound thought experiment reveals that the universe is governed by laws of physics that can create objects of a density that is almost beyond the limits of our human imagination, a quiet and humbling reminder of the sheer beautiful power of gravity. The baldness of a black hole, as elegantly described by the no-hair theorem, is a profound and poetic statement about the ultimate simplicity of these cosmic objects. The theorem suggests that once a black hole settles into a stable state, it loses all of the complex and intricate details of the matter that created it or fell into it, the specific chemical composition of the star that collapsed, the unique orbital mechanics of the planets it consumed. All of that beautiful and specific information, the hair, is lost forever behind the event horizon. From the outside, The black hole can be described by just three simple properties: its mass, its spin, and its electric charge. It is like taking a collection of beautiful, unique, and intricately carved wooden sculptures and casting them into a single perfectly smooth bronze sphere. The sphere has its own weight and its own spin, but all of the beautiful individual details of the wooden carvings are gone, their unique stories melted down and absorbed into a final, simple, and perfect form. The baldness of a black hole is a quiet and profound statement about the universe's ability to erase complexity and return to a state of a symmetric and beautiful simplicity. At the very edge of a black hole's event horizon, the inward pull of gravity is so overwhelmingly powerful that it creates a cosmic waterfall in the very fabric of space-time itself. Here, space is flowing inward toward the singularity at a speed that is faster than the speed of light. This is why nothing, not even a beam of light that is pointed directly away from the black hole, can ever hope to escape. The light is like a powerful expert swimmer trying to swim upstream against the current of an impossibly fast-moving river. No matter how fast the swimmer moves through the water itself is carrying them backward even faster, and their ultimate destination is inevitably downstream. The event horizon is the precise point where the river's current first exceeds the swimmer's maximum speed. This beautiful and profound analogy reveals that the event horizon is not a place where light is pulled back, but a place where the very stage upon which it moves, the fabric of space-time itself, is being pulled inward with a gentle, silent, and unstoppable force. While black holes are often portrayed as cosmic predators, a direct head-on collision with a stellar mass black hole is an incredibly and almost vanishingly unlikely event. This is due to the simple and profound fact that space is, for the most part, almost completely empty. The distances between the stars in our galaxy are so unimaginably vast that even with billions of silent, wandering black holes, the chances of our solar system ever happening to cross the path of one are practically zero. A black hole's powerful gravitational influence is only a danger when you are very, very close to it and the cosmic roads are incredibly wide and clear. It is much like trying to imagine two single specific grains of sand, separated by miles of vast empty desert, ever happening to touch. While it is not a theoretical impossibility, the sheer, beautiful emptiness of the landscape makes it a practical one. This profound and comforting emptiness is the universe's greatest and most gentle shield, a silent and beautiful guardian that keeps its most powerful and wonderful creations a safe and respectful distance apart. The gravitational field of a supermassive black hole is so immense and so far-reaching that it can act as the gravitational anchor for an entire galaxy. These cosmic titans, residing at the very heart of most large galaxies, including our own Milky Way, are the central point around which billions, and sometimes trillions, of stars gracefully orbit. While the black hole's mass itself only accounts for a tiny fraction of the galaxy's total mass, its incredible density and central location make it the perfect, stable pivot point for the entire, vast, and spiraling structure. It is like the simple, silent, and incredibly strong hub at the center of a colossal spinning wheel. The hub itself is small and unassuming, but it is the anchor point that allows all of the beautiful intricate spokes and the vast sweeping rim to spin in a ballet, perfect, stable, and harmonious motion. In this quiet and profound way, the universe's most powerful agent of consumption is also its most patient and effective architect, a silent and gentle giant that holds the very cities of the stars together. Black holes are far more than just cosmic curiosities. They are one of the key and most essential puzzle pieces in our quest to understand the grand, sweeping story of the universe's evolution and its ultimate, final fate. By studying how they form, how they grow, and how they interact with the galaxies they inhabit, we can learn about the very processes that have shaped the cosmic web we see around us today. They are the engines of the most luminous objects in the universe, the architects of galactic structure, and the final silent resting place of the most massive stars. They're also the place where our two most successful theories of the universe, general relativity and quantum mechanics, come into beautiful and profound conflict, pointing the way toward a deeper, more unified understanding of reality. They are like a single, ancient, and mysterious Rosetta Stone discovered in the vast, silent desert of the cosmos. On its surface are inscribed the secrets of the universe's birth, its life, and its ultimate, quiet, and beautiful end, and in its elegant and simple laws we can read the story of everything. When a black hole is disturbed, either by consuming a star or by merging with another black hole, its event horizon can ripple and vibrate, much like the surface of a still pond after a stone has been dropped into it. The study of these specific and predictable vibrations, a field known as quasi-normal mode analysis, is a powerful tool for understanding the fundamental properties of a black hole. Each of these ring-down waves has a unique frequency and decay time that is determined solely by the black hole's mass and its spin, a beautiful and simple cosmic chord that contains all the information about its source. It is like listening to the pure, clear, and fading tone of a perfectly cast bronze bell. From the exact pitch of its song and the precise duration of its hum, a skilled bell maker can tell you everything there is to know about the bell's size, its shape, and the metal from which it was forged, without ever needing to see or touch it. This gentle cosmic ringing is the unique and beautiful song of space-time itself, a quiet and profound echo of its most violent and transformative moments, a final, fading whisper from the heart of the abyss. Stephen Hawking's groundbreaking work on black holes represents one of the most profound and beautiful achievements in the history of science, for it was the very first time that the two great pillars of modern physics, general relativity and quantum mechanics, were successfully united. He showed that when the strange probabilistic rules of the quantum world are applied to the powerful, curved space-time at a black hole's event horizon, a startling and beautiful new phenomenon emerges. The black hole is not entirely black, but must emit a faint thermal glow, now known as Hawking radiation. This was a moment of deep and beautiful synthesis, a single, elegant idea that bridged the vast, conceptual gap between the world of the very large and the world of the very small. It was like a linguist discovering that two ancient, seemingly unrelated languages, one spoken by giants and one spoken by elves, actually shared a single, common and beautiful root. This profound and quiet act of theoretical unification did not just change our understanding of black holes, it changed our understanding of the universe itself, revealing that even its most disparate and contradictory laws must, at their heart, be part of a single, beautiful, and unified song. In the vast and beautiful cosmic zoo of galaxies, astronomers have discovered a strange and asymmetric class of objects known as ultra-compact dwarfs. These tiny, dense galaxies are thought to be the final, beautiful remnants of much larger galaxies that have been stripped down by cosmic collisions. In these violent gravitational encounters, the larger galaxy's outer starry halo is torn away, leaving behind only its dense, bright, and resilient core. At the heart of this surviving remnant is the original galaxy's central supermassive black hole, now surrounded by a tight, compact cluster of its most loyal and closely held stars. It is like a beautiful, ancient, and majestic tree standing alone in a vast open field. A powerful storm has swept through, tearing away all of its leaves and smaller, outer branches, but the strong, solid trunk and the few, thick, inner limbs that are closest to its heart have remained, a quiet and beautiful testament to its enduring strength and its deep, powerful roots. These beautiful, tiny galaxies are the cosmic equivalent, a silent and profound reminder that even after the most violent and transformative events, the universe has a beautiful and quiet way of preserving the very heart of what once was. A black hole is fundamentally invisible to our eyes and to our most powerful telescopes because it does not emit or reflect any light of its own. It is an object of perfect and absolute absorption. Any light that happens to fall upon its event horizon is not scattered, bounced, or reflected, but is instead captured by its immense gravity, its journey ending in the silent, one-way passage to the singularity. This makes a black hole a true anomaly in a universe that is otherwise filled with objects that we can see, either by the light they create, like a star, or by the light they reflect, like a planet or a moon. A black hole is the cosmic equivalent of a perfect, theoretical blackbody, an object that absorbs all of the electromagnetic radiation that falls upon it, of every frequency and from every angle. It is like a small open window into a vast, completely dark room on a bright and sunny day. The window itself does not have a colour. It is simply a portal to a place where light goes in but never comes out. And so, against the bright wall of the house, it appears as a patch of perfect, silent, and beautiful black. Every black hole is a profound and beautiful reminder that the universe is governed by laws far more extreme and wondrous than our everyday intuition can ever hope to comprehend. Our human experience is built upon a world of gentle gravity, the steady and predictable passage of time, and the solid, reliable nature of the ground beneath our feet. But a black hole is a place where all of these familiar comforts are stripped away, revealing a deeper, stranger, and more fundamental set of cosmic rules. Here, gravity is not a gentle pull but an absolute master. Time is not a steady river but a flexible and flowing current, and matter is not solid but is crushed into a state of infinite and beautiful silence. Our intuition is like that of a person who has lived their entire life in a single quiet room, understanding only its simple straight walls. A black hole is the first glimpse through an open window into a vast, curved and beautiful landscape of mountains, oceans and stars that they never knew existed. They are the universe's quiet and gentle invitation to us, a call to embrace the beautiful and profound mystery that lies just beyond the comfortable shores of our own understanding. Our gentle journey through the cosmos has brought us back from the edge of the abyss, from the silent, velvet darkness of 100 different truths about black holes. We have drifted through regions where time itself slows to a near standstill, imagined the final, brilliant scream of a star being consumed, and listened to the faint, cosmic echoes of two ancient giants merging into one. We have seen that these profound and beautiful objects are not monsters, but are a natural and inevitable consequence of the universe's most fundamental laws, a quiet and elegant expression of gravity's ultimate power. As we now leave these wonders to their silent, patient existence in the cosmic dark, let the vastness of these ideas be a gentle reminder of the beautiful and profound mystery that surrounds us. May these thoughts of cosmic grandeur bring you a sense of peace and perspective, and may your own journey into the quiet darkness of the night be a restful and rejuvenating one. Sleep well,